Good afternoon, and welcome. According to your programs, I am Armando Machado, and I'm here to introduce Peter Killeen. I first met Peter, I didn't know Peter was going to be on the stage when I wrote this introduction, so I could be in big trouble. I first met Peter about 25 years ago. I was a graduate student at the University of Florida. A group of us traveled to Chicago to a MABA meeting at the time, and we decided to blow off the afternoon and go to the art museum, where we happened to run into Peter Killeen. And Peter had just published the arousal paper, so he was a clear and rising star, and we were quite impressed, quite relieved, actually, when we went over and introduced ourselves to him, and Peter actually appeared to take a sincere interest in who we were and talked to us and asked us questions. And that initial delight turned in about 30 minutes to a feeling of complete physical and mental exhaustion as we tried desperately to keep up with this madman who was engaged in some sort of Markovian steeplechase through the museum, going from painting to painting and from topic to topic, and bombarding us with questions and ideas that we had never considered before. And my brain basically exploded. 25 years later, I am proud to say that I still feel pretty much the same way. I spend most of my time trying to keep pace with Peter Killeen. Peter sees the world differently than I do, for sure, and I think than most of us do. He sees it in bigger chunks. He sees the grand vision, and yet he's able to distill from that an essence that he can turn into simple and elegant models. But even that's not enough for Peter. It's important for Peter that those models have an exposition which is equally elegant and pretty, almost musical at times, like lyric poetry. And so it seemed appropriate in this introduction to use a little poetry. And given Peter's ancestry, the form of the poem was pretty much a given. A lad there once was from Tempe, for whom temporal events did seem key. From his most, excuse me, I knew I was going to do this. Yeah. A lad there once was from Tempe, for whom temporal events did seem key. From his most animated espousal of coupling and arousal sprang IRTs, parties, and the occasional striptease. Ladies and gentlemen, Peter Killeen.
Hey, thank you. I really appreciate that. Thank you, Greg. It's hard to get going now. Here to talk about response rate. And I guess the first question is why? Why am I here to talk about it? But also why response rate? Why do we care about response rate? Why do we use that as such an important dependent variable in our field? An honest answer for most of us would be because we inherited it. It's what our mentors used. It seems to work, and we can publish if we use it as a dependent variable. But there are problems with it. And I want to first review the problems and then the promises of it. And I would like to try and leave us with a sense of the rightness of rate, why it is right, what it is good to use for, and how to get from it to more fundamental measures. More than 50 years ago, Skinner said the task of an experimental analysis of behavior is to discover all of the variables of which probability of responding is a function. Probability of responding, not rate of responding. And yet he and many of us after him use rate. But rate has problems. It's not always a good measure of response motivation. Various actions work best at various tempos. When the Pointer Sisters moaned, "I want a lover with a slow hand," they did a better job than I. They weren't calling for a depressed or disinterested or disengaged lover. Speed doesn't tell all. So why do we use it? It's not even theory-free. How do we calculate it? We measure responses over time and divide by time. Why do we divide, and how much time? How do we decide on these things? What are they? Michael earlier talked about them being the shadows of departed inter-response. Responses were the shadows of departed inter-response times. What's going on between responses? That's where the action is, some people think, myself included, or a lot of the action, not all of it. Rate is the parameter of a population. There's a lot of inter-response times that comprise rate. If we look at individual inter-response times, once again, Michael Davison showed that not each band of inter-response times is affected the same way by response rates. So it's a mishigas. Let's look at some. At the first panel on the left, a representative summary statistic, a distribution of inter-response times. The data were collected by Lauren Kettle from a rat on a fixed ratio schedule, fixed ratio 80. And the x-axis is time since the last response up to a little over a second there. And the y-axis is the number of observations at each of those inter-response time bins. Now, that's a very skewed distribution, as IRT distributions usually are. And when you see distributions like that, right away, if you're teaching statistics, you say, well, you don't want to use a mean on something like that. That would be very misrepresentative. It might give too much weight to the tails. You might want to use another measure of central tendency, like, maybe median. But nobody uses median IRTs. I once tried using geometric mean IRT transformation because I thought that the tails were causing too much influence on our measures, and got nothing interesting out of geometric means. We seem to limp along with averages, even though looking at the distribution, the tails of the distribution are exerting undue influence, it would seem. So with all of these issues that can't be we've been lucky with our rate as a dependent variable, but how can we resolve them? To do so, we need some kind of theory, some set of goals and some set of models that will help us achieve those goals. Despite Skinner's choice of probability of responding as the thing to be predicted, he and Förster also claimed our basic datum is the rate at which a response is emitted. Such a datum is closely associated with the notion of probability of action. And a few years later, frequency of response is valuable just because it provides a basis for the concept of probability of response, a concept towards which science of behavior has been groping for many years. And this will be my argument or conclusion also, that we measure rate of responding because it's a very efficient way of learning something about probability. And it's the probability that we're learning about is the probability of being engaged in a particular action at a particular time. When you measure probabilities, you always have to define the sampling space, as Armando made clear. What are you counting, and what are you counting in, and what are you counting out? There are no unconditional probabilities. All probabilities are probabilities given. The probability of it's going to rain, given that it's tomorrow, given that we're in San Francisco. So there are always givens that have to be stated. Well, when you're talking about the probability of responding, it's probability given what? Your sample space could be something like 2 pigeon keys. The probability of making a response on the left key, then you're looking at relative response rates. This was something Skinner didn't want to do. He rejected relative response rates as a dependent variable. Tolman did well with them, and Skinner and Herrnstein reintroduced them very profitably. We're not going to look at relative response rates in that sense today. Another way to do it is the way that Alliston will be talking about in an hour, and that is looking at sequences of responses and asking what's the probability of a particular sequence amongst all possible sequences, or as Armando did of choosing arms in a maze. But if you don't do that and you want to look just at responses in time, the free operant, how do you choose your sample space? What are you selecting from? Conditional on what? Well, there's always time. In fact, that's about all that's left to us. So we could say, what's the probability of observing a response in a small interval of time, which we will talk about today. Or we could say, what's the probability of emitting a response in a small interval of time, given that it's delta seconds since the last response? That is, the probability of a response is a function of time since the last response. We'll be talking about that today, too. In fact, let's consider a very special case. Let's look at the probability of responding in time on the assumption that it's constant. What would the distribution of inter-response times look like if the probability of responding at any instant is constant? Well, in fact, the first picture is consistent with that curve. If you forget about the first bar on it, you can fit an exponential decay function to that curve very well. What's very special about an exponential decay function is that it's the unique solution to the problem of what would an IRT distribution look like if responses were invariant in time. So it's a very fundamental null model. We don't know anything. We're not predicting a change. Rates are not going to go up in time. They're not going to go down. All we know is they're going to exist at some rate lambda, we'll say. If you think that might be happening, or if you want to say, it's not happening, but I want a good null hypothesis to counter it with, then the exponential distribution is forced. And it actually predicts behavior very well in this first curve with some, whoops, this does, do I pull the trigger for? Okay. It predicts the behavior very well in the left figure. Another way of looking at it, though, is to look at the response rate as a function of the number of opportunities for responding, because long after the prior response, there's not so much time left. So if we want to measure response rates in time as a function of time since the last response, we can do a transformation known as a hazard function, which I'll describe in more detail in a few moments, or an IRTs per op distribution. If behavior is constant in time, that curve should be horizontal. These are the same data in the middle panel, and you see after the first second or so, the curve that describes the data is a horizontal line at a rate of 0.47. So that's another way of saying that a null model that behavior is constant in time is relatively decent for these data. But look, the leftmost graph is an IRT distribution, and that only goes up to a second. And the last bin on the right is all of the other responses. When we represent the things we average over the calculator rate, that is IRTs, in the standard IRT distribution, we're focusing on a very important but small part of the range. And that's the most frequent responses that occur very quickly. And we're throwing out into a dump bin all of the ones that recur after that. If we look in the middle graph of the same data, there are lots of data way out at long IRTs. Their probability is low, but they take so long to emit, they contribute very heavily to our measure of responding. So what I'm going to do is move on to talk about why we are interested in probability rate. And then I'm going to come back to these distributions and tell you how to calculate them and why you want to. For instance, I'll be telling you that the parameter of this, there's a unique parameter for this curve on the left that describes it. And it's the mean of the distribution, or the rate of emission, lambda, of the exponential distribution, the single parameter. And the most efficient way of measuring the parameter of this distribution is to count the number of responses emitted in time and divide by time. So if responding at a constant rate is a decent description, constant probability over time is a decent description of the data, then A, you force an exponential distribution, and B, the most efficient maximum likelihood measure of that is response rate, the way we've always calculated it. So insofar as this is a valid representation, then what we've been doing all along for rates is a good way of getting a handle on it. And you'll see that it is, except for not out here in the 1 to 10 second range where maybe most of the action is. So to get into this, I'd like to first present a little data to operate on, and then we'll come back to the analysis of response rates. These are data collected in a very simple paradigm. 10 seconds on, 10 seconds off of a key light, responding on various schedules when the key light was on, pigeons in all of the experiments. If an animal did collect a reinforcer during the trial was terminated, and recording was. And we measured latency, the time between the between the trial onset and the first response. The probability of responding on a trial at all. Here, the animal responded on this trial, obviously. The probability of responding within a small epoch of time, randomly sampled from this trial. The response rate, once the animal had started responding, the run rate, and the response rate over the whole trial. And the reason we did this, we wanted to know, at least for pigeons and Skinner boxes in this paradigm, what the relation, before we started seriously studying response rate and latency, we wanted to know how that related to the other typical dependent variables that are measured and represented here. And so to find that out, we used this paradigm and disturbed responding in many different ways. And I'm going to run through them, the first slide slowly and the rest of them very quick because they're boring. What in this case we did, we reinforced animals on VI schedules of between 2 minutes and 960 seconds, which meant 1 or 2 reinforcers per session, and measured response rates. Each column is a different pigeon. The first data point is base rate, and then after that, these were sessions of extinction. The rightmost column is the average over animals. So where the pointer is now is the base rates for responding on different VI schedules. You'll see even though response probability was even though reinforcement probability was low, the animals responded at it with very high probability. The first row shows the probability of responding. So this is like Leslie's work shown yesterday, that when you have this on-off paradigm, you get very high probabilities of responding, even when rates of reinforcement are low. But rates of responding decreased over sessions of extinction. Latencies, which are reflected here in 1 minus relative latency. We wanted things to change in the same fashion here, these to decrease with time. Latencies didn't change much under these operations. They will under others. B is rate of responding once a response has been made, run rate. And that decreased a bit with extinction. These are session averages. Most of our analysis, we looked at trial-by-trial data. These are session analyses. And overall response rate, this sort of compendium of them all, changed nicely over extinction sessions. This was VI, base rate, and extinction. Other manipulations included variable ratio schedules with extinction as the disturbing operations. That was satiation. This was extinction, variable ratios and extinction. Satiation on fixed intervals. Extinction on fixed intervals. So the whole point of all of this was to disrupt and get differential changes in these dependent variables, and then to see how one was predicted from the other. Scott Hall, who can't keep away from analyzing data. Are you here, Scott? I think I saw you back there. You wave to us? There you are. Put his hand down now. You'll never know. But Scott can't stop analyzing data, and he loves collecting it too. And he said, well, let's do a principal components analysis. I said, well, okay, and he did. And then a confirmatory factor analysis. What the purpose of those were to see whether there is a simple underlying process that accounts for a lot of the variance in the way these variables covary. Having done that, you go back and ask, using this structure, can you then predict the relationships of one from another? So if you have, with principal components, so you have one component. We called it strength here, but we don't want to push that name. You can call it anything you want. We found that there was a very strong correlation, predictability, between overall probability of responding on a session and overall response rates. But there were strong correlations with run rates and latencies also. That was for the first set of the slides I showed you. And another set, the data looked just like it for another subset of the slides. So the point of all of this is that these dependent variables hang together. They're measuring similar sorts of things. Skinner's right that probability and rate are talking about similar sorts of things. And having validated that that was the case, in a few cases, latencies went in a different way, but that was rare. Generally, things hung together. The literature says that effortfulness of responding is not going to hang together the same way. Having validated that we had coherent phenomena here that are dependent variables related, our next question was, and the one I'll be spending most of my remaining time talking with you about, well, what causes response rates to be the way they are, and how can we talk about them, and how can we relate them to probability of responding? Well, here are IRT distributions again for pigeons. And the x-axis is the inter-response times on the 4 different pigeons from some of the data that we presented earlier. And the y-axis is the relative frequency, which could be interpreted as a probability, if you cared to, of finding a response in one of these bins. And these were 1-second bins under a variable interval schedule here. Most of the responding occurred in the first, had an inter-response time of 1 second. No surprise there. Now we get to a deep point. How do you analyze data? Well, it depends. It depends on what questions you have. You could do something like this, and a very simple model would predict this inter-response time distribution. Just a geometric progression fits these data perfectly. But if you look at a finer grain, like half-second distributions, then you find that whereas a geometric distribution handles these data sets nicely, we will see that a simple geometric decrease is not happening because there's a lower bin here. Or you could get more refined or more refined and more refined. So the answers you get depend on the questions you ask, and the questions you ask can be more or less detailed, and it depends on what you want to pay in terms of parameters for describing these. Let me show you some simple machines that will describe them at least at the first 3 levels of analyses. These are machines. Now, as John said, he didn't really think the x-axis was memorial strength, and he showed that you didn't have to think of it that way by blanking it out, so it could be anything. But he really thought it was memorial strength. But that's just because it's easy to think of things, and if you're careful, you don't get in trouble doing it. So I don't really think there are machines like this inside of the head of our animals for those ABBA people that just wandered in here and are about to take a front. But by building machines that do things the way that our animals do, it clarifies in our head. Einstein said that explanation is reducing a phenomenon to another we already have intuitions about. So here are some simple machines that you can have intuitions about. The first is a simple process where you come in, you start a counter, you wait, you loop until time has elapsed. Like anybody that's written a computer program, you hang in a while when loop or a do loop until time has elapsed. As soon as delta seconds has elapsed, you make a response. And then you go back, reset the counter, do it again. This generates responses that go like this. Just simple cyclic machine. The one below it makes it a little more interesting. It adds probability. It waits until delta seconds have elapsed, and then it says with some probability p, emit a response. And so what the graph shows is, the figure shows, whoops, am I shooting myself? No. There we go. Loop until time's elapsed, set a probability gate. If you set it to 1, make a response, otherwise go back. In either case, reset time and go again. And so this will give you, it sounds, I actually have a tape of it, but I didn't bring it with me. It's also very dull, like a sputtering So you can set up this system yourself. One easy way to set it up is to plug in a pigeon, because this is not a bad model for very basic inter-response times for pigeons, and even better for rats. Here are 4 rats, again, data collected by Lauren Kettle, responding. I believe this was another fixed ratio schedule. And these are IRT distributions. And the curves shown through the data, except for the first point, are exponential decay functions. So these IRT distributions are well defined, described by this hypothesis, null hypothesis of constancy of emitting behavior in time. The stochastic cyclic machine would generate data like these, except for the first bin. What's happening in the first bin? Well, that's down around less than 1/10 of a second. In fact, it's measured by this first parameter. So this is like 0.05 seconds for this guy, I can't quite read it, 0.06 or so, 0.04. So there's a little bit of a gap here where something is not right, but otherwise it's exponential decay. Well, what could not be right there? What could not be right is the fact that it takes him a second if he hits the key to get his head back off the key again and go through the process. Or in this case, they're rats, lever pressing. Getting that lever to really depress takes a little extra a tenth of a second or so. Very simple process that I'll model in a minute. But to do it effectively, I'd like to introduce a new construct called a CBM, a clocked Bernoulli model. And this is what I was just doing here. It's flipping a coin every X seconds. And I don't think that there is a device for this in the statistical literature because it blends two things, a probabilistic event, the probability that the coin will come up heads over here, with a timing device here that only lets you flip it every delta seconds. So this is what I call a clocked Bernoulli model. It's a clocked one because it waits tau seconds to do something. It's a Bernoulli model because this generates a Bernoulli sequence of, and all that means is what happens if you flip a coin probabilistically. If you flip a coin and note whether it's heads or tails, that's a Bernoulli process. So this is flipping a coin at measured intervals, a CBM. It's our basic module for IRT distributions. So now that we have this, we can put two CBMs together and we'll generate all of the interesting IRT distributions with one exception that's very important that I'll come to at the end. So if we just loop here and if we set the parameter q to 0 and are just going through this one CBM, it will generate the exponential decay process we talked about, which is our basic null model. If, however, we force the animal to go over here, or if we do it at a high enough rate, it'll look exponential. If we do it at a low rate, it'll look geometric. No difference, really. If we come over here first and say, no, it takes me, a quarter of a second to get my head off the key, and then I can go back again. So every time a key peck is made, there's a dead time of a quarter of a second. It gives us precisely the model you saw. Oh, here I've simplified it down for the rat data I just showed you. So here, there's a single parameter for this. You're flipping a coin so fast that you keep only one thing invariant, and that's the rate of flipping it. It's very fast. And then you come back, and with a probability of 1, you pause for delta seconds. So what I call a shifted exponential model. It's shifted because it doesn't start at 0. It starts to the right of 0. And it accounts for a lot of data. I'll use it later as my basic way of getting back and forth between probability and response rate. So here is an IRT machine that is sort of a classic machine, exponential distributions that are shifted from the origin by delta seconds. And that's what gave these, so two-parameter models. Now we're going to see data that depart from these somewhat systematically, more or less systematically. These still account for a lot of the variance in the data. So when we talk about models of what's going on, I'll often default to this because even though it's not perfect, it's good enough for government work. Well, here's a case where with one situation, these are or lag diagrams. Bill and colleagues did some lovely ones of these, and they showed ripples like these. If our birds were behaving like rats, the data would all look like this bird 95 at the bottom, where the probability of making a IRT of a particular length on one interval is plotted against the probability of making one of that length on the other interval. Brief IRTs are the most common. Long ones are infrequent, but there's no other pattern in the data. But if you look at this guy, he's got his hair in bangs. You know, there's just all sorts of ripples here. What's going on there? Well, as Bill pointed out, there's some periodicity in responding. So this guy deviates from the basic model we were talking about. Plotting them in standard IRT distributions, this was the bird on the bottom that looked something like a rat, simple shifted IRT distribution. This was a bird that gave us all of those ripples. And a model suggested by Bill Paglia, I call it a Paglia machine, does very well for these data. It's not perfect. It's missing one little bump here. It's a kind of model that would also account somewhat for Michael Davison's data, but not at all perfectly because he's got other things that are going on in his distributions that I'll come to later. What's happening here with these pigeons is that we've got a IRT machine in which the animal will make a response with the same old probability, and essentially they'll miss the key. Those secondary bumps that we saw were off-key pecks, I think. This key peck was missed, so this other one at twice the period of this one came up. This other mini bump came up here at 3 times the period. So if what's going on with pigeons is that they're responding like rats, except they've got a tighter distribution on their timing than this, and they miss the key occasionally, you'll get the kind of distributions representative of what Bill Polya showed. And you can get this also out of these 2 CBMs hooked together with minimal other assumptions. Here's some licking data collected by Mark Riley. 2 rats licking a drinking tube, generating distributions of interlick intervals. And if you fit this simple Polya machine, which essentially is saying they're licking at a relatively constant rate with some wobble, but occasionally they'll miss, with some low probability, they'll miss a lick, do an air lick, and you'll not register it. It accounts for these data very nicely. Well, these distributions are all focusing on the left tail of the distribution. Let's see what I wanted to say about these. Okay. So here we have our basic models for analyzing response rates. Why analyzing response rates? Because rates are composed of collections, aggregations of inter-response times. To get a sense of whether what you're doing with rates is correct, you look at the collection. How do you look at the collection? There are different ways to do it. One is the standard IRT distribution. That's what we've been talking about all this time. There are other ways, though, that are maybe better. You could fit this very well with these shifted exponentials, which is cool, if that's what you're magnifying by the way you describe the data. Another is to look at the constancy of responding in time. Here are the same data plotted a third way. They're called survivor functions that Rick Shull has been popularizing lately, and reasonably so. These distributions also go way out to 8 seconds and give a nice and different picture than the first, certainly. This distribution, a survivor function, asks what the probability is of witnessing an inter-response time that's greater than some value, and that value is plotted on the x-axis. So the probability of witnessing an inter-response time greater than 0 seconds, if you've got a bunch of inter-response times, is going to be 1.0, and that's the topmost point. The y-axis is a logarithmic scale. It's a logarithmic scale for a couple of reasons. One, there's a range of probabilities to look at here, but a better reason is if this model is true, then this curve should be a single straight line in these coordinates. And it is mostly a single straight line, but by gosh, it bends over and becomes another line here. That's because there are 2 regimes in this data that you miss completely in the IRT distribution. IRT distribution takes you up to about a second. And you can see in the hazard function, there's a lot of action here until it settles down to another constant rate. So what's going on if you look at it this way, which is very easy to plot, and at the end of the hour I'll give you access to a spreadsheet that's on a SQAB website that will do all of these analyses for you. What you have here, if you just take all of your responses and plot them, and you can do this in Excel very easily, such that on the y-axis you have the logarithm of the probability of seeing a response greater than t, and on the x-axis, t. This is a cumulative distribution function just flipped over and put on a semi-log axis. You get 2 straight lines. The first one, or more, or fewer, the first one talks all about the IRTs that you'll be finding in a standard IRT distribution. That's time on task and characteristics of hitting the lever when the animal's in it. Rick talks about it as responding within about. Michael Davison talks also about it as time engaged in this task. He finds other little bumps in this function, which with the kind of data he's got, you can find. But for this animal on a fixed ratio, essentially the animal is responding pretty strongly in the range of 0 to 1 seconds with high probability repetitiveness. Then he was going, "Ay," and then coming back. And this distribution of sojourns from responding was also a constant probability, just a different constant probability of hitting the key when he was at it. And so this right-hand distribution is picking up the second tail here. So survivor plots, we'll come back to them in a bit. If what the animals are doing is working on a standard response with a exponential clock Bernoulli model here, a little dead time when a response occurs, and with some probability quitting and coming back to the task, then this set of CBMs describes the behavior, and it gives the broken stick or the two-legged aspect you saw in the prior graph. So this, I would like to think, is really the basic model for inter-response times, rats and pigeons, and I think humans also, of a particular constant. Now, it doesn't have to be constant, but that's a good null hypothesis. If you want a null hypothesis, you'll assume an exponential distribution. And so a constant probability while they're on the task of emitting the response, and a constant probability of breaking from it and coming back to it. And that gives you the right-hand distribution or something like it. The amount of time it takes to make a response, delta, if that is playing a substantial role in what's going on, will be shown by an offset of the curve. It will come up to 1, not quite at 0, but at maybe a tenth of a second to the right of 0. So you even pick that up in this display. So that's a good way of doing it. Okay, I want to shift from IRTs to RTs, response times. The principal dependent variable in cognitive psychology is response times. There's lots of models of it. Race models such as Ratcliffe's are very successful. They're basically simple intuitions of random walks until you generate enough data to make a decision. Fun stuff to look into and to see how to use with pigeons and rats and people. If you want to look at latencies, post-reinforcement pauses, the same CBMs, clock Bernoulli models, give standard versions of those. A well-known distribution that fits a lot of data is a gamma distribution, where the animal essentially can be viewed as a machine that moves from 1 through n states. And it moves through those with constant probability. And so essentially it flips a coin until it's time to go to the next state, flips a coin until it's time to go to the next state, flips a time until it comes in, and then makes a response. If there's only one state, then it's an exponential distribution. If there are 2 states, it's a very skewed exponential distribution that starts at 0. If there's 50 states, it's a normal distribution. So this is a very standard model for latencies. It's a good model to know. Another one is sort of cool. It's called an extreme value distribution. It's what happens if events are rare. They require a lot of rare events to happen, and they all happen. It's a good model for earthquakes and for floods and other kinds of extreme values. Extreme because they're rare. For cancers also, because cancers often require 4 or 5 improbable events to happen. And as soon as the last of those improbable ones happen, you get a symptom. So in Gumbel machines, you've got these CBMs lined up in parallel. And once all of them have set, you exit. Another version of Gumbel machines is you have them all lined up in parallel, and once at least one of them is set, you exit. Those give distributions that are very good for modeling PRPs. These are latencies in some of the studies that I was showing you, latencies for the first response. And I think these are gamma distributions, but they could be Gumbel because they fit equally well. By the way, a lot of people helped Scott and I, and then later Mark and Lauren and I, write these papers. Greg Galbica was one of those. Tony Nevin was another one. Armando Machado. A lot of, science is a community process, so all the stuff you're seeing here got shaped up by help from all the people here. So once you understand clock Bernoulli models, you also have access to good models of latencies, and they tend to be correlated with response rates and probabilities, and so that's good. First, I'll show you what this will do to justify your interest in it. If you look at the probability of responding on a trial, it was extremely well predicted in all of these studies by just looking at the probability of responding on the prior trial. Here is the predicted on the x-axis and the observed on the y-axis probabilities of responding on a trial. Down here, they're so glommed together, we've blown up the axes to show you these data here. This is excellent prediction. How do you get it? You say that animals in all of these situations that we showed you earlier did this simple thing. If they had responded on the previous trial, then they'd come back and respond on the next trial. There'd be at least one response with a probability of 96 for these set of data. If they did not respond on the prior trial, then the probability of responding on the next trial was just 0.37. So it was a two-state Markov process. And that's what described data so beautifully here. So it just mattered whether they're in the mode. And this gets back to the bout thing and the non-bout. Essentially, bouts can get spread over trial sets. So essentially, if the animal was in the response mode, the bout mode, you'd know he's in because he's responded on the prior trial. He's most probably still in. He'll most probably respond again. If he didn't respond on the prior trial, he's probably in the sojourn from responding. And those combinations do a fine job in predicting the data. At this point, the short attention span is starting to drop out. Well, hold on, because we're going to show the most important take-home message of an equation, a very simple equation that will permit you to go between response rates and response probabilities. And it's important not just for theoretical reasons. It's because often we collect data with one, and we want to know the other for very good reasons. And this gets you back and forth. And why am I showing you that? Oh, okay. This is the simple shifted exponential model. Constant probability of responding, but if a response occurs, there's a very brief dead time before it gets back in the saddle. I'm assuming that for the following. If you take a stream of behavior that's generated by a machine like that and randomly sample an epoch of capital delta seconds. I'm sorry about the two deltas. This is little squiggly one is a small delta is how long the dead time is, how long it takes to get their head off the key or lever. The capital delta is the observation epoch. If it doesn't take them any time at all to make a response, and you ask, at a given response rate, if you sample for, let's say, 1 second, what's the probability of seeing a response in that time interval? Then, as response rate increases here, probability increases also. And this is a simple cumulative exponential model. If it takes a while to make a response, there's a simple modification of it that you can see in JAB last year to correct for this dead time. Essentially, it subtracts out the dead time from the response stream. And you get a range of curves that range from cumulative exponential to essentially a straight line, depending on how long it takes to make the response, depending on how extended it is. This is the fundamental relationship between response probability and rate, this equation. This is the one that Skinner was looking for. And insofar as the simple shifted exponential model is correct, and we know it's not perfect, but it's a good description of a lot of data, then you can go back and forth between probability and rate with this model. To give you an example, when I asked Scott to say if he could randomly sample thousands of trials, blah, blah, he said, yeah, and it was done in a minute. And this is the result. This is from some of the data we showed you earlier on of response rate on the x-axis for the same 4 pigeons, the probability of seeing a response during an observation interval of 1 second in the center set of columns. Each bird took a different amount of time to peck the key. And so there's a single parameter that's slightly different amongst these 4 birds. But that's held constant in everything I'll show you here. If you change the observation interval to half of a second, the probability of observing a response will be lower, but it will increase with response rate according to the same curve. If you give them a 2-second observation interval, you'll often see responses occurring with high probability. It will still covary with response rate according to the same function with the same parameters. This is how you get back and forth from probability to rate. They're both good. Now this is on run rate. Let's suppose you take the same thing with the same parameters on overall response rate, you get the same picture. It's easy. In fact, you could set small delta to 0 from most of these and still account for a lot of the data if you didn't want a free parameter. So that solves the problem of how to go back and forth between response rate and response probability. But why would you want to do that, and what would it tell you? Well, you could put all these things together. Why would you want to mess with response rate if I keep talking about response probability? Response rate is the most efficient way to get an estimate of the key parameters in response probability. That is the probability of emitting a response at any point in time. So what we've shown is that Clock-Bernoulli model is a simple version of what it takes to generate lots of distributions of time, of events in time. You can concatenate them, that you can represent latencies, probabilities as gamma distributions comprised of CBMs, probability of responding on trial as a second-order Markov process, and rates, or IRTs, as Poisson processes. That's the shifted Bernoulli. This was the take-home equation, where response probability is mapped on response rate. And I want to show why this is important. I only have a couple of minutes left. I want to show why it's important to do this. I did a study with pigeons responding on auto-shaping, negative auto-maintenance. These guys went forever. You know, thousands of trials. Each time they responded, they precluded reinforcement. But pigeons hang in there. Thousands and thousands of trials. And in collecting these data, in many conditions, I collected the total number of responses in the 5-second interval before they might have gotten fed. But any response would mean that they wouldn't get fed at the end. And so the question is, with a very simple model of what was, I could predict the probability of what was going to be happening here from one trial to the next with a very simple model, essentially an exponentially weighted moving average, linear average. But I had a richer data than probability. I had response rates. And so on the x-axis is the predicted probability of making a response, and the y-axis is the mean response rate. And the solid curve on the bottom is this model that maps from one to the other with no free parameters, with 0 time to make a response, assuming the full 5 seconds. And this is another assumption. Essentially, what this shows is that if you want to make predictions using probabilities, which could be a good thing to do, you can get to them to rate if you want. More importantly, rate is a very good way to measure probabilities of this scale because it doesn't saturate. Response probability saturates too easily. And so you can go back and forth from one to the other. So why do we measure response rate? It's a good dependent variable. It varies in lots of ways. But mostly, I think, because it's a very good way to be calculating what the probability the animal is engaged in a behavior. This is something even Billy Baum would agree with. What we're looking at, it's not a fundamental datum in its own right. It's what we measure in that sense. It's fundamental. But we're really looking at the probability of being engaged in a task. The survivor analyses can give you that. And so in all of these cases, now we can be at leisure to record what we want, measure what we want, and get to the other. Finally, what I want to do is show you a machine that you can use. There we go. This spreadsheet's available on the SQAB website, and it does these analyses for you. It's a good way to get your feet wet. What you do is you select one of several models, or there's a sheet here in which you can take all of your own data and throw it in, and it will do these analyses for you. And it gives simple IRT distribution. It gives a hazard function that's normalized in a convenient way. And it gives a log survivor function. This was for a shifted exponential set of data. You can fiddle around with it if you want and change parameters in the distribution. But it's not going to let me do that now in the time I have left. But you can play with it. And you can see the x-axis offset is giving you the amount of dead time it takes to make a response. It relates it to the CBM, gives you summary statistics, and shows you this is the signature for a shifted exponential model. If what you're interested in is what I call a show machine, and Rick blanches each time I do, another sheet lets you play around with the parameters and see what the signatures in terms of IRT distribution, hazard functions, and the dog-legged function is. And there are poly machines. These are the pigeons pecking at a key. You'll get lumpy IRT distributions because here's where they missed a peck. The hazard functions also are non-homogeneous in time. But it turns out that the survivor functions are noisier in a sense, but are still well fit by this kind of a model. So download it from the site and play with it. And then in the last sheet, you can put your own data and see what they look like and see if they map against any of these models. Sorry that I took so much time, but I'm finished. No, I don't think it would. The question is, if you find order at one level of analysis, why would you want to switch to another? In particular, if you found orderliness, and as someone earlier said, but it's an old saying, so I don't have to remember who it was, science is the search for invariances. If you find invariances with one level of analysis, you'd be foolish to give it up to go to another. But there's a one-to-one map here between response rates and probabilities, so you would preserve the order. Maybe the mode of describing it would be simpler in one than the other, but these are doppelgangers. You can go back and forth. You lose nothing. It's not right to say one is right and the other is not. I like to think right now, this month, this year, that probability is the fundamental variable, just the way Skinner did, and now I know how to get there with the most efficient measure, which is response rate. I'm real happy with that, but I'm happy about predicting one or the other. So it doesn't matter. We've got both. But you're right. If you find that order emerges most regularly or most strongly on one level than the other, you go for that. Yes, from the back.
You alluded briefly to the role, I think, of response duration, and thinking the parameter was Q in one of your models. It seems that the experimental analysis behavior is focused on very short duration responses. In human research, we oftentimes are looking at much longer duration responses. Can you talk about
Yeah, absolutely. Let me preclude you here because we're running. But yeah, the whole problem there are a lot of problems in generalizing from Skinner boxes to the real world, or the other world, Stu. And so one of them is clearly extended responses extended in time. And I think Rick Shull's and Michael Davison's also notion that we're really looking for bouts or nested bouts of behavior on or off key. Once we realize that, then we realize that also the extended bouts of humans, whether they're drinking at a bar and you're looking at, you can see what I'm thinking of, the rate at which they lift up the glass, or if you're looking at how likely they're being in a bar, all of these are nested, and I think a similar analysis would work. You just have to be flexible about which is getting nested inside of the other.